So question 5b, we'll do question 5b and question 5c at the same time now. So question 5b says calculate the values of the system's DC gain, k, when s equals 0 and the time constant tau. Okay, so from question 5a, we had the transfer function. We simplified the transfer function to being 2 over 4s plus 23. Okay, so to find tau, we need to get it in the format of a numerator over the time function tau s plus 1. So to get it into that format, we simply divide everything by 23. So we have 2 divided by 23 over 4 divided by 23 s plus 1. So we can simply find the gain of the system when s goes to 0. That would be 2 divided by 23 over 1. So the gain k is 2 over 23. Oops, 23 that way. And tau is 4 divided by 23. Okay, which if we calculate that out is 0.173. And k here is 2 over 23, which is 0.086 or thereabouts. Okay, so that's part B. Now part C asks for a table. So complete the missing columns in the table below into your answer booklet. So we've got time in versions of tau. So we've got 1 tau, 2 tau, 3 tau, 4 tau, 5 tau. Okay, let me just switch pens and I'll fill it on here. Obviously you'd answer this in your own answer book, but just to make it simple, I'll put it on here. Okay, so 0 lots of tau is going to be 0. 1 lot of tau is going to be 0.173. Okay, 2 lots of tau is 0.346. 3 lots of tau is going to be 0.519. 4 lots of tau is going to be 0.692. 5 tau is going to be 0.865. Okay, now I haven't actually given you a value for k. If you wanted to do it quite simply, you could just assume that that's 1. That's okay. But what I'm going to do is take a bit of a shortcut, because part D is saying plot the response of the systems to a step input of 5 units. So sorry, not k, input, theta input. Normally you assume that to be a step input, which would just be 1. But since we're going to say that it's an input of 5, we could shortcut that and say that this is going to be 5. We know the value of k, so we calculated that already as 0.086. So what we're going to do is simply multiply these out. So 0 is 0 there. 0.63. So here we have 0.63 times k, which is 0.086, and then times 5. Okay, because this is going to help us solve part D. So if I do that, then this would be 0.2709. The next one would be 0.86 times k, which is 0.086. No relevance there. Multiplied by 5, so that would be 0.3698. Next one along would be 0.4085. Okay, like that. And then we've got 0.4214. Okay, and then 5 lots of that, we have 0.4257. 0.4257. So that's filling in the missing columns. Okay, now to plot a step response of this, again, you'd do this in your own answer book. Okay, so a step response assumes that we have a immediate input to the system. And what's the final value going to be? Well, the final value is going to be is when s goes to 0, and that's going to be the final k value, multiplied by 5. So that would be 0.086 times 5. Okay. Let me just calculate that one. So that would be, final value would be 0.086 times 5 is 0.43. So I could actually say 0.43 and that final one there. Okay, so what have we got? We've got time values here. So we've got 0 lots of tau. We can just do the time values in versions of tau because that's what we've calculated it. So 1 tau, 2 tau, 3 tau, 4 tau, 5 tau. Okay, and we have here something that we've calculated already. So it would be output, which would be looking at that table above, 0.2709. Okay, 0.3698, 0.4085, getting a bit tight here, 0.4214, and 0.4257, 0.4257. Hopefully you'll do it a bit neater than me. Okay, so at 1 tau, we have this value here, 0.2709. Okay, at 2 tau we have 3698. At 3 tau we have 4085. At 4 tau we have 4214. 4214. Okay, and at 5 tau we have 4257. Okay, which looks like that. So you know that it's a first order system, so it should have a step response that follows what we've been seeing. So it sort of starts quite quickly. Obviously this would be a bit more linear. I haven't done it very linear here, but you get this shape, and then it bottoms out really at 0.43, and that's the step response graph of what I want.